In this presentation, we will look into cohesive laws and try to build some intuition around how cohesive laws are defined and why. Cohesive laws are commonly defined to model fracture and failure in continuum and as well as in adhesive joints. In finite element models, what happens at the tip of the crack can be very simply defined by this law. We will start from the analogy of failure in a tensile test. When an intact specimen like this is pulled in tension, initially the force response increases sharply and somewhat linearly. But as the cross-section reduces and the necking starts, the force starts to drop. Force further drops when the specimen starts to damage and fail and eventually drops to zero. Now if we convert this force into stress and isolate the blue curve, we achieve the cohesive law of failure for this tensile specimen. Note that in a cohesive law, in y-axis we have stress and in x-axis we have displacement. Notice this cohesive law is more curvy than we would like to model in finite element. One way to replace this curve is to use a triangle or bilinear cohesive law. During this process, we must be careful that the area under this blue curve is as close as possible to the area under this red curve. It is also possible to replace the original curve with a trilinear curve. This is commonly known as the trapezoidal cohesive law. Nevertheless, we are again careful that the area under this original blue curve is as close as possible to the area under this trapezoidal curve. Let's for now only focus on the bilinear cohesive law. Area under this triangle can be defined by the width and height of the triangle. The unit of the area will be stress multiplied by displacement, which is energy per unit area. Notice that energy per unit area is the unit for fracture energy. But just knowing the width and height of a triangle is not enough to completely define a triangle. For example, there could be another triangle with the same width and height, but it would be totally different than the original triangle that we drawn. So we will start with defining this first line. We can define this line by knowing this slope and then knowing the maximum height that it reaches. So far the required parameter to define the line is the slope and the maximum stress. Now if we know the width b, we can complete this triangle. Usually from the experimental test, we get the area under this curve, which is the fracture energy. So knowing the fracture energy or the area under the curve and also knowing the height already, we can calculate for the width b. And by that, a triangular cohesive law is completely defined by three parameters: the slope, the maximum height it attains, and the fracture energy. But in practice, there are more than one mode of fracture. This figure shows that mode 1 and mode 2 fracture has their own triangles. Similar is true for the mode 3 fracture. So to complete the definition of cohesive law, we have to construct three triangles. For simplicity and commonly, same triangle is used for all modes. In softwares like Abaqus, we can define the slope for three modes as 3 elastic traction. Notice that they can be different or they can be same. Then you can define the maximum stress for different modes. Here the maximum normal stress is defined to be equal in all three modes. Finally, you have to define the fracture energy. It can be defined as mode dependent or mode independent. Mode independent would mean that fracture energy is equal, or in other words, the area under each curves are equal. Here I have defined a mode independent definition of cohesive law. Hence only one value of fracture energy. Instead, if the fracture energy is mode dependent, you have to define three different fracture energy, representing the area under each curve. To know more how a triangular or a trapezoidal cohesive law is defined in Abaqus, please check the link in the description.